Hello, class. Welcome back. This is lecture 2. Today we're talking about limits of sequences. So last time we talked about sequences, and now we're going to think about the limits of sequences. And it's best just to see it through example. So let's think about 3 sequences. So because I have 3 of them, I'm going to use A, B, and C to describe them. So AN, BN, and CN will be my 3 sequences. So the first one will just be an alternating 1, -1, 1, -1, forever like that. The second one will be denominators with power of 2 on the bottom, 1/2, 1/4, 1/8, 1/16, and so on like that. And the third will just be adding 3 each time. And so you get something like this. So we want to think about or consider what is a sequence going toward. So for example, AN, it just flips back and forth. Between 1 and -1. So it doesn't really go toward a single number. It has to go towards one number. It does sort of go towards 2 numbers at the same time, but we really want it to go towards 1 number. And it does not do this. Meanwhile, BN does. So it's actually this sequence. If you, as I said verbally, it's this 1/2 to the n. And this does go towards something. If you think about what happens when you have tiny fractions, so maybe like on a graph or something, if this was 1, if you plotted 1/2, 1/4, an 1/8, a 16th, as you moved down towards the right, it would be getting closer and closer to 0. But it would have never actually touched 0. So we would say that this does go towards something. It goes towards 0. Never passing it or touching it, but it does go toward it. And then CN is actually just starting with 1 and adding 3n to it. It just grows forever. So it does not go toward a number either. And you could sort of try to visualize it a little bit. It just goes up and up and up forever. So it's not really going towards a number. And you can see that even just from here. If you just keep adding numbers, it just goes up forever. It doesn't go towards a single number. Okay, so we have names for these situations. So AN and CN are examples of divergent, is the word, divergent sequences, meaning that they don't go towards something. And BN is an example of a convergent sequence, which is the opposite situation, where it does go towards something. Now, going towards something, we had a phrase for this in Calc 1 that we're going to bring back now. So that we're really talking about limits here. Something we learned in Calc 1, but for functions. And now we're doing it for sequences. So in general, this is how it works. If the terms of a sequence, we'll just call it AN in general, not specifically the AN from before, just any old AN sequence. If they become closer and closer to a number L, we say that AN is convergent or converges. And L is called the limit of the sequence. So whatever number it actually goes toward, the sequence goes toward or converges to is called the limit. And how do we summarize all this in a quick mathy way? So what do we write to mean this? We write limit as n goes to infinity, because the sequence is a bunch of terms indexed by n, and an is the nth term. So as n goes to infinity, this is just saying you're going down the list of numbers in the sequence. As you go forever, you get closer and closer to L. So we say that the limit equals L. Okay. So then if an is not convergent, so it has no limit here, then it's called divergent. Okay, or it diverges. You can also say that. All right, so let's see some examples of this stuff. So there is a much more formal definition of limit of sequences that we don't deal with this in this class, but it's out there. If you want to be very official and fancy, you can look it up. But you'll learn that in a much later class if you stick with math long enough. But for now, we're just going to think about it like this in a very vague way. So let's decide whether each sequence is convergent or divergent. So this is a very typical type of question for this section. So you're just given a sequence, and we don't have very many tools yet. So we're just sort of looking at it and thinking about it, really. We haven't developed tools yet. We will. But for now, you just want to sort of identify what's going on. And the last one will be Cn. Let's do this. 1 3/2, 9/4, 27/8, and so on like that. Okay. So let's think about these examples here. Maybe I'll just number them. 2, 3. Okay, so for 1, just sort of looking at it, I can see, but that's because I have lots of experience, that it looks like it's going towards something. But how can we actually check it? Well, let's think about if we write out the pattern. So what is the pattern here? Well, on the bottom, it's just powers of 2. And if I start counting from 1, then the power of 2 on the bottom starts at 1 as well, because a 1 is really 2 to the 1 on the bottom. Now the top is a little bit trickier, but it's always, if you notice, it's always 1 less than the bottom number. So it's going to really be, you can think about this as 2 to the 1 minus 1. And then a2 is 2 squared on the bottom, but it's really on the top, that same number minus 1. So on the top, you get 2 to the n minus 1. So one way is to think about, what is this doing? And this goes towards 1. So you can see that the numbers are slowly getting closer and closer to 1. And we'll have an official tool to show this later. But for now, it's just enough to sort of look at it and think, okay, yeah, it's going towards 1. So this goes towards 1. And so we write something like this. The limit as n goes to infinity of an is 1. To answer the question, it converges. Okay, so for 2, so again, we'll have detailed tools for this later. So for right now, it's a bit wishy-washy, but you just sort of want to think about it. So for 2, let's think about if we can establish a nice pattern. So we have -1, 1/2, -1/3, and then I believe it's 1/4. Yeah. So we can sort of see the pattern here, which is that the bottom is just growing and it always equals the index. So this is really an n on the bottom. And then on the top is always just 1, but it flips back and forth between positive and negative. And if you did the lecture problems from yesterday, you know, the trick to that is multiplying by a -1 to the n, but then making sure that it matches whether it starts at negative or starts at positive. So for example, if I plug in 1 here, I better start off as negative, which I do. So it matches. So this is the correct thing here. So this limit, this one is also going to converge. And what's happening is it's going towards 0. You can sort of think about it visually. So like -1, 1/2, -1/3, 1/4. So it sort of bounces back and forth while going towards 0. So this guy converges to 0. And again, we'll be able to really show this later. But for now, we're just sort of thinking about it and writing down the answer. So this is equal to 0 because the numbers go towards 0. They're shrinking while switching back and forth between positive and negative. So they're going towards 0. Okay, and then for Cn, let's try to establish the pattern here. So C1 was 1, C2 was 3/2, C3 was 9/4. So what's happening here is that the numbers are growing. It's hard to tell because they're fractions, but they are actually growing. And one way to see that they're growing is to, again, think about what is Cn. Well, the bottom is just powers of 2. So this is 2 to the 1. This is 2 squared on the bottom. This is 2 cubed on the bottom. So it's always 1 less than the index. And then on the top is powers of 3. And it's the same thing, 1 less than the index. And so because you can write this as 3/2 to the n minus 1, this will just grow forever. So the trick there is that if you have a number bigger than 1, and you do powers of it, it's just going to grow up and up and up forever. So this guy diverges. So you don't say that it has a limit. Okay. So what other things can happen? So before we learn the actual strategies, let's think about some properties that show up. So what happens if we take a convergent sequence. And we just change it a little bit. So let's change it like this. So something that was convergent, 1/2, 1/4 powers of 2 on the bottom, like this. This converges to 0. But let's change it. Let's just put some numbers at the beginning. Let's put a bunch of 7s at the beginning. 7, 7, 7, 7, 7. And then it's the same. So does this guy converge still? Or does it now diverge? Well, it still converges to the same thing. And that's because convergence is all about what happens over here at the end. What's happening as you go toward infinity. And the numbers still go towards 0. So the point is, it's as you go to infinity, the numbers do still go towards 0. Yes, the first 5 numbers don't go towards 0, but in the end they do. And that's what matters for convergence. What about if I change it in this other way and I just put a 7 in between every term? Well, now it's actually going to diverge, because as you go forever onward down the list of numbers, it never goes towards 0 because it keeps popping back up to 7. So the terms never go towards 0. They jump back up to 7 every time, every other term. No matter how far you go, they never start going towards 0. Okay, so now let's bring in the tools to actually calculate these things. And we're going to bring tools from Calc 1. Okay, so we're going to use them to determine convergence or divergence. And so here's the trick. If you have a sequence AN, you can just sort of replace it with a function that matches it. So for example, if I'm looking at this sequence, so this is really just 1/n, where n starts at 1. So that's the same. Oops, it's the same as this function. Where they match what you plug in. So when you're only plugging in these numbers, they're exactly the same thing. But in calculus, we learned how to take limits of things like this. So in calc, you could do this. And you learn that it's 0 because the bottom grows forever, making a very tiny fraction shrinking towards 0. So in Calc 1, you just do that and you're done, and that's the limit. So because they match, let me write it like this. They match whenever x and n are the same thing, then they have the same limit. So So this guy will also be 0. So then this guy converges to 0 too. So again, visually, it's a little bit easier to see. So the idea is that if you're only plugging in whole numbers to 1 over x, then you get something like this. And that limit goes to 0. And that's exactly the same thing as 1 over n. So this, in Calc 1, you learned that this red line goes to 0. And in Calc 2, you learned that these dots go to 0. That's the idea. So the trick is to just replace and with a matching function. And then do that limit. With Calc 1 tools. So you really just change it into a Calc 1 problem every time. Okay, so that's the idea. I guess I could, yeah, we'll just do examples. Okay. So let's do something like this. So here I'll just skip ahead and give you the formula for AN instead of making you work for it. And then why does this converge? It's because if you look at the function 1/2 to the x instead of the sequence 1/2 to the n, that converges. When you do the limit as x goes to infinity, back in Calc 1, you learned that this goes to 0 because it's just a fraction growing. The denominator is growing and the numerator is not, so it's just going to 0. Okay. So in general, let's try to solve like a more general problem. So what values of r make r to the n converge? So we just saw if r is 1/2, it converges. But we want to know like what's like the borderline, because really any fraction has the same property. The bottom is growing more than the top is, so it goes to 0. So r equals 0 works too, because you just get 0, 0, 0, 0 forever, so it converges to 0. R equals 1 also works. You get 1, 1, 1, and so on forever. But if you go past 1 to like 2, then it's going to diverge, because now I get growth past any number. So I get 2, 4, 8, 16, 32, and so on. So now it does not converge. It diverges. So in Calc 1, you might say that the limit is infinity, but we're not saying that yet here. We're just going to say it diverges because it just grows and grows. Just grows forever. Okay. So you need, the key is you need fractional numbers. You need numbers beneath 1 to make this work. So in general, this guy converges for if you're between 0 and 1. And then it'll diverge when you're past 1. If you plug in a number bigger than a fraction less than 1, then it's just going to grow and grow and grow forever. Okay. So now anytime you see a fraction to the nth power, you can just do it. No work necessary. You just say it converges if it's less than 1, and diverges if it's above 1. But what about something a bit weirder? So here, you'll notice that I'm just going to be giving you the formulas like this one and the previous one, instead of writing out the list and making you find the formula, because it's just a big hassle. So in general, we just like to work with these straight away. And just it's more interesting to think about. Okay. So what about a sequence like this? So it's 2/3 to the n plus 1/4 to the n. So from above, we know how these sequences behave individually. So this guy, if it was just this guy and just this guy independently of each other, they both would converge because they look like r to the n with r between 0 and 1. So they both converge independently. So how do I deal with this where I'm now adding them together? Well, luckily we can borrow some Calc 1 knowledge about limits. So luckily there are properties of limits coming from Calc 1. So you just have to worry a little bit about a couple of things, but here they are. So given two convergent, so they got to already be convergent independently sequences. If you have two that you know are already convergent alone, that means that they both have limits. If you write it out like this, so maybe I'll call this one A and the other one B. If you know for a fact that they have limits independently, then we can conclude a bunch of stuff. Number one, we can add the two limits together by doing them independently. That's what this is saying. So immediately we could go back to this problem and say that this converges to 0 because independently, if I call this one AN and this one BN, this goes to 0 because it's just fractions less than 1 shrinking down to 0. This one goes to 0 for the same reason. So then if I take the limit of them added together, I just add the limits and I get 0 plus 0 is 0. So this guy does converge to 0. So the other way to think about this property is just that you can separate limits through addition. You can sort of think about it as you can either add the limits separately or together, but they have to individually converge in the first place, or else this doesn't work. So if one of them did not converge and the other one did, then you can't do this. This would not help you. Okay, limit. You can also do multiplication. Again, but they have to both converge. You have to know that they both converge, and then you can do this. And then division also works, but you have to worry about dividing by 0. So you could do this one and this one independently. and just divide the limits. As long as you aren't dividing by 0. So b can't be 0. Okay, so for example, now we could use this in a few examples real quick. So if I do 1/4 to the n plus 2/3 to the n, this converges since what? Since I can independently verify that the two pieces of the sum converge. This one goes to 0 from before, because it's like r to the n with r less than 1. This one goes to 0 for the same exact reason. So I can just add the limits together and say that that's what this converges to. Okay, that's the addition property. The multiplication one. If I want to know, like, what about 1 over n squared? Because I already know about 1 over n, we did that one earlier. Well, I can think about it as multiplication between two 1 over n's, and then this will converge to 0 times 0, because each individual one converges to 0. So notice that this wouldn't work for something like this if I did like n cubed times 1 over n or something. This does not work because this guy is infinity, so does not is not a number L. So because this one doesn't converge, diverges, we can't do this separation thing. Of course, in this example, you wouldn't need to, because you could just cancel and simplify it. But the point is, you can't separate it unless they both converge. They need to both converge for you to be able to do this independently. So, but sort of going along with this one, you could do the same thing for any power of n on the bottom, because you could write it as a bunch of 1 over n's multiplied together. So k times in this case. So this will also converge to 0. So it's for the same reason that 1 over n squared did. It's because you can separate it into pieces and just multiply all those zeros together and get 0. So 1 over n to the 5th, 1 over n to the 100th, whatever power of n you want on the bottom, those will all go to 0. Okay, so now let's see a couple more examples. I have to think about what we're going to do later. Okay, I think I want to remind you about L'Hopital's rule. So recall L'Hopital's rule for functions before we do these examples. Because we often turn our sequences into functions and we do these instead, we need to remember probably the most useful tool. This doesn't have to be infinity. This could be this. So if this equals infinity over infinity, or 0 over 0, then what you can do is you can take the derivatives of the top and bottom to figure out the limit that you're looking for. Oops. So just keep this in mind that this could come in handy in these examples, because once you turn your sequence into a function, you're basically back in Calc 1. And so you're allowed to use all those rules that you learned back then, which you may not remember because it's been a while. But just keep that in mind because I'm going to reference them. Okay, so let's determine if each sequence is convergent or not. All right, so 5 minus 3 over n squared. So you can sort of think about this in two ways. One is to separate it into two pieces. So this is really just the limit of 5, and then the limit of, with a negative in front, of 3 over n squared. The limit of 5 is just 5. So if you just do a bunch of 5s, you get 5. And then this is, it's got an n squared on the bottom. It's got just a 3 on the top. So you can take out the 3 if you want, but that's a little bit of extra work. You can really just say that this is going to be 0. So then because the two pieces converge independently, then you can say that this converges to 5 minus 0. So it's minus here. And it's because of this work here. Or the other option is to use functions. So this is using sort of the rules we just learned and remembering what I just did about n squared, but it's sort of easier just to always do functions as long as you can. So, or consider just a function 5 minus 2 over x squared. And then this limit, you're allowed to just use Calc 1 rules, which are very quick, which is that the limit of a number is just a number, and the limit of 2 over x squared, because the x grows on the bottom and the 2 doesn't grow on the top, is just going to give you 0, and you get 5. So that's another way to say that it converges to 5, because the function that matches it converges to 5. The sequence automatically does too. Okay, so then another example where you can't really just use the rules I was talking about because you end up dividing by 0. So if you just tried to separate this and say, well, I can just do division independently, and you said like this, I'll do this one, and then I'll do this one. Well, this one is 0, which is bad because you're going to divide by 0 if you try that, to just say that this converges to blank over 0. That's already bad. But then also this one diverges on the top because it grows. So you can't even separate it in the first place. So none of that is going to work very well. And so this is where going back to Calc 1 stuff really comes in handy, and you can use L'Hopital's rule. So what you do is you just consider this other limit where you replace the n's with x's, and you think about this. So this goes to infinity over infinity because x is going to infinity. So both the top and the bottom are growing very big. And so now I can use L'Hopital's rule, but I got to remember a little bit about derivatives. So this limit now is going to equal, the derivative of 2 to the x is, it's like an exponential, so it stays the same, but you have to multiply by ln of the base, and then x squared becomes 2x. And then this is still infinity over infinity, just growing on the top because of the power of x, and on the bottom. So if you do it one more time, then it works out nicely. So you take another derivative, you just get another ln of 2 here. But on the bottom, you get rid of all your x's. So now only the top grows to infinity. So you'd say that this limit is infinity, but what does that mean about our sequence? We don't say that the sequence goes to infinity, we just say it diverges. So that we just say this, because it doesn't go towards a number, we're just going to say 2 to the n over n squared diverges. So other examples where you might need to use L'Hopital's rule. Well, if you see a fraction like this, you pretty much have to. So this will work very similarly. You consider the function instead of the sequence. If you do L'Hopital's rule, you're gonna have to do it twice. But as you do these, you start to realize that powers of x grow much more slowly than exponentials. So again, you can only do this because it is infinity over infinity. So you take the derivative, you get 10x on the top. Derivative of e to the x is e to the x. You do it one more time because it's still infinity over infinity. And you just get 10 over e to the x. Now the x is only on the bottom. So the bottom is growing very big while the top remains the same. So you're just going to head towards 0. And so you can say that this converges to 0. Okay, so it's very important to have this sort of summary that you know that you're talking about the sequence, and you're just using the function stuff as a tool to tell you about the sequence. So you got to say at the end what the sequence is doing. Another type, something like this. Same thing, you're going to consider the function, take that limit. But in Calc 1, you learn a nice trick to do these pretty quick, and it comes from L'Hopital's rule, so you don't have to just do it 4 times. You can just say like, okay, yeah, this is infinity over infinity, or maybe even, yeah, it's infinity over infinity, but it could be negative, that'd be fine. Infinity over infinity still would work. But what you learn in Calc 1 is if I just do L'Hopital 4 times, the lower power of x's and the numbers, when I take their derivatives, they'll eventually be gone. And I'm just going to end up with the powers of the biggest powers left. And so all I have to do, the trick is just look at their coefficient. So it's going to be 3 over -4. So that's the trick you learn in Calc 1. And so this guy converges to -3/4. So that's if the power is matching, because they both have a power of 4. But then there's other things. If the power on the bottom is bigger, it goes to 0. Power on top is bigger, it goes to infinity. So other rules like that to remember. But in any case, for this one, this converges to -3/4. The last one is the trickiest one. So there were other tools in Calc for limits that are long gone, but gotta remember them. So again, we're going to consider the function and the limit. Well, we're just going to say it all at once by doing this. And here we need to use our Calc 1 brain. So we got to remember logs to do this kind of limit. So here's how this one worked back then. You would set this equal to some other variable, whatever you want to set it to. I'll call it y. And then you would take the log in order to bring down that power of x. Whoops. Put that limit in there, sorry. So you don't have to do this many steps. But the point is that what you end up looking at is this limit. So now I can bring that x down because of log rules, and I have multiplication instead of power. And then to use L'Hopital, it needs to be infinity over infinity or 0 over 0, which it's not right now. Because right now this x goes to infinity because it's just x, so it grows as x grows because it's the same thing, so it goes to infinity. This guy goes to 1 over infinity, which heads to 0. But then you get ln of 1, which is 0. So you really get 0 times infinity, which is not what we want. And so what you learned in Calc 1 was to use algebra to manipulate this a little bit. And so you take that x and you say x is the same as dividing by 1 over x. And now the top, that still goes to 0 because that's what this was. The bottom now goes to 1 over infinity goes to 0. So now you can use L'Hopital's rule. So much to remember in this problem. You need to take the derivatives independently. Derivative of ln of something is 1 over that something times the derivative of the inside. The derivative of 4 over x is negative 4 over x squared. And the derivative of 1 over x is negative 1 over x squared. So those are going to cancel nicely to make it a little bit easier, but this still takes a long time, unfortunately. So you're just going to get negative 4 over 1 plus 4 over x, I believe, as long as I've done my algebra wrong. Oh, okay. Let me just think about it. Yeah. Okay. So then this is just going to be, okay, as x goes to infinity, this guy just goes towards 0. So you just get negative 4 over 1. So that's the limit of ln of y as x goes to infinity. So y equals negative 4 with an e on it to get rid of that ln. And so finally, this guy converges to that. Okay, so that is going to be it for today. A lot of Calc 1 stuff to remember for these types of problems. Okay, see you next time.